Now let's look at an example of how we might interpret a multiple regression equation. Right, so here's our normal multiple regression equation. Y hat, the expected value of y, is equal to b sub 0 plus b sub 1 times x sub 1 plus b sub 2 times x sub 2 plus yada 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 plus b sub j x sub j. Right, and we interpret this the same way. This is the expected value of y. This is the y-intercept, a scaling number. This is b sub 1. This is a partial rate of change for x sub 1. The partial rate of change for x sub 2, all the way out to the partial rate of change for x sub 3. These are our regression weights for each of our predictor variables. Let's talk about how that might be interpreted. I'm going to use an example here, again, made up numbers, but this is an example of how we might use GPA, high school GPA and SAT scores to predict college performance, right? You can see where this would be a legitimate concern for admissions officer. So let's say I'm an admissions officer, I'm trying to predict college performance based on high school performance. I look at GPA, I look at SAT scores, and I collect all of these data, and then I analyze those data and come up with some regression equation. And the equation I come up with is that my expected college GPA is equal to 3.96 plus 1.23 times high school GPA plus 0.002, kind of running out of room there, times SAT score. Right? And so this equation is the same way. Here's my, excuse me, I shouldn't have written it that way. This is my expected college GPA. 3.96 is my y-intercept. I can't interpret that. That's just a scaling variable to get everything on this side into the proper scale so I can get an outcome here. 1.23 is my partial rate of change associated with high school GPA, and 0.002 is my partial rate of change associated with SAT scores. Now, how do I interpret that? Remember before with bivariate, this was about a rate of change. In multivariate regression, it's a partial rate of change. What that means is I have to hold everything else constant. For every single point increase in high school GPA, I expect a 1.23 increase in college GPA, holding SAT score constant. That's the important part here, right? So it only works if I compare two students who have the exact same SAT score. If they have the same SAT score, then if the second student has a 1 point difference in GPA, I can expect a 1.23 point increase in college GPA, but only for two people having the same SAT scores. If their SAT scores are different as well as their GPA, all bets are off. Well, I won't say all bets are off. It's just the interpretation is different. It can't be that same kind of interpretation. Likewise, holding GPA constant, holding high school GPA constant, I can expect for every single point increase in the SAT, I can expect a 0.002 increase in college GPA. Again, that only works, that interpretation only works that way, holding high school GPA constant. This is why we call it a partial rate of change. Now, here's the interesting thing here is look at these numbers, right? 1.23 for high school GPA, 0.002 for SAT scores. That's because these are on different scales, right? SAT score, I have no idea how it works now, but it's like 800 to 1600. That's the way it was when I was young. And then GPA, right, is on a 4-point scale. These are two completely different scales. I can't really compare which one's more important. I don't really know here, right? Because I have a scaling issue. This is why we have the standardized regression equation. This is when that comes in so handy. So if I was going to create a standardized regression equation, that would actually look like this. 0.56 of the z-score of GPA plus 0.34 of the z-score for SAT. Now I can make some comparisons here. Right now here is beta sub 1, right? That's associated with your high school GPA. And here, 0.34 is beta sub 2, which is associated with SAT score. I can see now that I can interpret these better. I can compare them to each other, right? So I can say that the partial rate of change associated with high school GPA is 0.56. That's a lot more than the partial rate of change of SAT scores, right? Standardized. So now again, it's still partial, so that part still stays the same. It's still holding SAT scores constant. Now remember this part, a standard deviation change in GPA, in high school GPA, results in a half of a standard deviation change in college GPA. Likewise, holding GPA constant, a standard deviation change in SAT scores can account for a 0.34, basically a third of a standard deviation change in college GPA. Right? And so now I can interpret these. I can say this results in a half of a standard deviation difference. SAT score only gives me a third of a standard deviation difference. I can say that GPA is a stronger predictor than SAT scores. Almost twice as strong, right? Because this is actually an interval scale, so I can make those kind of assessments. It's almost twice as strong of a predictor. This is the power of that standardized regression equation, is now I can make those kinds of statements. Up here, super confusing because it's all about scale. Once I standardize it, I can compare 0.56 to 0.34 and I can say this is the better predictor. Now, just because that's the better predictor doesn't mean I drop out SAT scores. In fact, if I drop out SAT scores, because you can imagine, we'll get to this later, SAT and GPA are probably related. If I drop out SAT scores, that's going to change the predictive ability and how GPA predicts my college performance. Likewise, if I were to drop out GPA, that would change this number. That would change beta 2 because our SAT score would be different there. There may be value here. In fact, there probably is a lot of value here. I don't necessarily want to drop out an additional variable just because it's not as valuable as the other one. I want to include both of these. Then I'm going to assess how well these together predict my college performance rather than just one of them at a time, right? And that's the value, that's the usefulness of multiple regression analysis.